This is Anuka, Agile Systems and AI provider. Welcome to Deep Learning series. Today's video is titled Deep Learning using CNTK. Today we will explore the most popular distributed deep learning framework of Microsoft, CNTK. It is now known as Microsoft Cognitive Toolkit. In this video, we will explore how to implement deep learning applications using CNTK and its various new features in the latest release. Furthermore, I will give an introduction to distributed deep learning techniques using CNTK. So let's start our journey of deep learning using CNTK with the introduction to CNTK. Microsoft Cognitive Toolkit. CNTK is a production-grade, open-source, deep learning library. CNTK embraces fully open development, is available on Github, and provides support for both Windows and Linux. This open-source deep learning toolkit was created by Microsoft speech researchers in 2012 and was then known as Computational Network Toolkit. Open-sourced on Github since January 2016 using MIT license. CNTK has 12,000 plus Github stars. It is third among all deep learning toolkits. CNTK has 140 plus contributors from MIT, Stanford, Nvidia, Intel and many others. The Microsoft Cognitive Toolkit is a unified deep learning toolkit that describes neural networks as a series of computational steps via a directed graph. In this directed graph, leaf nodes represent input values or network parameters, while other nodes represent matrix operations upon their inputs. CNTK allows users to easily realize and combine popular model types such as feed-forward DNNS, convolution net CNNS, and recurrent networks RNNS or LSTMS. CNTK implements stochastic gradient descent (SGD), error, backpropagation, learning with automatic differentiation, and parallelization across multiple GPUs and servers. CNTK is also one of the first deep learning toolkit to support the Open Neural Network Exchange (ONNX) format, an open-source shared model representation for framework, interoperability and shared optimization, co-developed by Microsoft and supported by many others. ONNX allows developers to move models between frameworks such as CNTK, CAF2, MXNet, and PyTorch. The latest release of CNTK supports ONNX version 1.0. For mission-critical AI research, CNTK team believes in efficiency and performance are important criteria. CNTK was designed for peak performance for not only CPUs, but also single GPU, multi-GPU, and multi-machine, multi-GPU scenarios. So now let me elaborate what is CNTK in general terms. CNTK can be defined as follows. CNTK evaluates and expresses nearly arbitrary neural networks by composing simple building blocks into complex computational networks, supporting relevant network types and applications. CNTK is production-ready, state-of-the-art, accuracy, efficient, and scales to multi-GPU or multi-server. A deep learning tool has balancing characteristics and it has the following features, namely, efficiency, can train production systems as fast as possible. Performance, can achieve state-of-the-art performance on benchmark tasks and production systems. Flexibility, can support various tasks, such as speech, image, and text, and can try out new ideas quickly. Inspiration of CNTK is from Lego's philosophy, that is, Each brick is very simple, and performs a specific function: create arbitrary objects by combining many bricks. Here we learn about CNTK functionality. CNTK supports development of deep learning applications on, first, CPU and GPU with a focus on GPU cluster. Second, GPU CUDA uses Nvidia libraries, including cuDNN-v5. Third, Windows and Linux. Fourth, automatic numerical differentiation. Fifth, efficient static and recurrent network training through batching. Sixth, data parallelization within and across machines with 1-bit quantized SGD. Seventh, memory sharing during execution planning. CNTK is highly modularized. It has well-defined separation of deep learning program into logical modules, namely, first, computational networks. Second, execution engine. Third, learning algorithms. Fourth, model description. Fifth, data readers. In CNTK, models can be described and modified with the following programming languages. First, network definition language NDL. Second, model editing language ML. Third, Python. Fourth, C++. And fifth, C# in progress. Let us see the list of CNTK applications. Many of the AI services Microsoft has are now created using CNTK. Cognitive Toolkit is the secret weapon for Microsoft to create cognitive services like Skype Translator, and many other AI breakthroughs like speech recognition that has now reached human parity for conversational speech. Some of the Microsoft apps that use CNTK framework are as follows. 1. Microsoft Cognitive Services. 2. Skype Translator. 3. Office. 4. Cortana. 5. Bing. 6. HoloLens. 7. Microsoft Research. 8. Windows ML. Here we go now and check out CNTK system support. CNTK is also one of the deep learning toolkits to support the Open Neural Network Exchange (ONNX) format, an open source, shared model representation for framework, interoperability and shared optimization, co-developed by Microsoft and supported by many others. ONNX allows developers to move models between frameworks such as CNTK, CAF2, MXNet, and PyTorch. The latest release of CNTK supports ONNX v1.0. CNTK supports most popular input data formats, namely 1. Plain text, for example UCI datasets. 2. Speech formats HTK. 3. Images binary. 4. DSSM file format. 5. New formats can be added by creating DataReader. CNTK has rich API support, mostly implemented in C++, train and eval methods. CNTK has low-level plus high-level Python API. CNTK has R and C# API for train and evaluate. CNTK provides UWP, Java and Spark support. CNTK has built-in readers for distributed learning. CNTK has Keras backend support. CNTK has model compression that is fast binarized evaluation feature. CNTK now supports CUDA 9 or cuDNN 7. CNTK support. The Microsoft Cognitive Toolkit. CNTK supports both 64-bit Windows and 64-bit Linux platforms. It is recommended you install CNTK from pre-compiled binaries. Now let's explore CNTK performance details. One of the advantages of Cognitive Toolkit is the way you describe deep networks, which are usually very complex as nodes on a directed computational graph with inputs and outputs. Once you've described a network, all the computation to learn the network parameters is taken care automatically, because you don't need to derive gradients or hand code the interactions between variables for backpropagation. You can create complex computational networks by composing simple building blocks. Cognitive Toolkit started as a framework for speech recognition, using not only the usual GPUs to speed up deep learning, but unusually, letting you take advantage of multiple GPUs on multiple machines to do distributed, massive scale deep learning. That way you don't lose performance or accuracy when you work with bigger data sets. Researchers at Hong Kong Baptist University are running regular benchmarks on the most popular deep learning toolkits CNTK, TensorFlow, CAF, and Torch, testing popular workloads, fully connected and recurrent neural networks, and two convolutional neural network architectures, AlexNet and ResNet. You can see on the slide the performance details of various deep learning toolkits. Image courtesy, https://thenwstack.io/Microsoft adds Python support, CNTK Deep Learning Toolkit /CNTK2 remains the fastest deep learning toolkit for distributed deep learning, claimed Wang, and I want to highlight the word distributed. Even on a single GPU, CNTK offers the fastest performance on both fully connected and recurrent networks. If you compare it with TensorFlow, on all four workloads CNTK is faster now. AlexNet, ResNet, recurrent networks, and fully connected networks, even on a single GPU. And when you scale up beyond one machine, that's where Cognitive Toolkit really shines, because many other tools can't even do that. When TensorFlow and CNTK was compared for performance benchmarking, team found that accuracy is mostly identical between the two frameworks. CNTK is faster at LSTMs or MLs, whereas TensorFlow is faster at CNNs or embeddings, but when networks implement both, it's a tie. Here in this slide we see CNTK performance details on AlexNet. On AlexNet, CAF is the fastest. On a single GPU, CNTK, CAF, and Torch display the similar performance. On Tesla K80, CAF achieves better performance than CNTK when the size of mini-batch is relatively small, while CNTK is slightly better with mini-batch size at both 64 and 128. On GTX 1080, CAF obtains slightly better performance than CNTK in all cases of different mini-batch sizes. Here in this slide we see CNTK performance details on FCNR network. On FCNR network, the size of mini-batch is set to 4096 in our test, and the results are shown in figure. We can see the speeds of CAF, CNTK and MXNet are very similar on a single GPU, which are slightly better than TensorFlow and Torch. With the number of GPUs doubled, the scalability of CNTK and MXNet are the best, and they both achieve about 35% speedup, while CAF achieves about 28% speedup, which is better than that of Torch and TensorFlow with about 10%. On a single GPU, the training with Torch is converged fastest. And CAF, CNTK and MXNet are faster than TensorFlow. When the number of GPU increases to 4, the convergence rates of CNTK and MXNet tend to be close to Torch, while CAF and TensorFlow are converged relatively slow. Here in this slide we see CNTK performance details on ResNet. As you can see in the slide, Torch is the fastest. In ResNet 56 performance benchmarking test, the mini batch sizes for ResNet 56 are 4096, 1024, and 128 respectively. In this larger size of network, MXNet achieves the best efficiency if there is only one GPU, while Torch tends to be more efficient on multiple GPUs. Regarding the convergence speed, MXNet and Torch have better results than the other three tools, and CAF is the slowest. Hence CNTK in orders of magnitude is better than all of the competition in LTSM. In this slide we go through the CNTK benchmark and comparisons. So performance-wise we can conclude that, if you want to run a small task on a single machine with and multiple GPUs, you can use any of those tools. But if you want to be serious about big data, scaling out to multiple GPUs on multiple machines, CNTK is the only one that offers that performance. CNTK has come a long way from 2016, its scalability has improved a lot. Let us study the CNTK scalability metrics. The full release of Microsoft Cognitive Toolkit 2.0 for use in production, grade and enterprise, grade deep learning workloads includes hundreds of new features incorporated since the beta to streamline the process of deep learning and to ensure the toolkit's seamless integration throughout the wider AI ecosystem. Some of the scalability characteristics of CNTK are as follows. First, CNTK is much faster compared to other popular deep learning frameworks. Second, CNTK can be easily scaled over thousands of GPUs. Third, Microsoft unveiled Project Brainwave, a scalable acceleration platform for deep learning, which can provide real-time responses for cloud-based AI services. For example, in China, medical intelligence startup AirDoc is using Microsoft Azure Cloud Services, Cognitive Services and Cognitive Toolkit for a technology that rapidly and accurately detects the onset of diabetic retinopathy, a complication of diabetes that can lead to blindness without proper treatment, from photos of patients' retinas. The recent enhancements for the CNTK had few great recent breakthrough in speech recognition, reaching human parity in conversational speech. The toolkit is used in all kinds of deep learning, including image, video, speech, and text data. Image courtesy, https://github.com/msrdl serving/infrastructure/wiki/tf vs CNTK performance and scalability comparison. From the graph, we have the following findings. First, CNTK shows better performance than TensorFlow on ResNet 18, say, 23% higher throughput with a single GPU. Second, both CNTK and TensorFlow scales, with CNTK scales better with more GPUs. In particular, with 8 GPUs, the throughput of CNTK is 41% higher than TensorFlow. These TensorFlow results are very similar as the TensorFlow results from Nvidia, in terms of scalability. Scalability lessons from CNTK. 1. CNTK makes better use of the GPUs via Nvidia APIs than TensorFlow does. That is why one GPU is better. 2. The numerical optimizations make a big difference in CNTK. You need to make sure that is turned on. Both TensorFlow and CNTK have gradient bit equals 32. Let us now understand how powerful CNTK Multi GPU Scaling is. CNTK delivers near-linear multi-GPU scaling, and was tested successfully with Cray supercomputers for 1000 GPUs. The Microsoft Cognitive Toolkit trains and evaluates deep learning algorithms faster than other available toolkits, scaling efficiently in a range of environments like from a CPU to GPUs to multiple machines, while maintaining accuracy. Nvidia and Microsoft worked closely to accelerate the cognitive toolkit on GPU-based systems and in the Microsoft Azure cloud, offering startups and major enterprises features like: first, greater versatility. The cognitive toolkit lets customers use one framework to train models on premises with the Nvidia DGX-1 or with Nvidia GPU-based systems, and then run those models in the cloud on Azure. This scalable, hybrid approach lets enterprises rapidly prototype and deploy intelligent features. Second, faster performance. When compared to running on CPUs, the GPU-accelerated cognitive toolkit performs deep learning training and inference much faster on Nvidia GPUs available in Azure N-series servers and on-premises one, for example, Nvidia DGX-1 with Pascal and NVLink. Interconnect technology is 170x faster than CPU servers for the cognitive toolkit. The recent experiment was independently conducted by Nvidia on its latest DGX-1 system, with CNTK showing more than a two-fold improvement over TensorFlow when 8 GPUs were used to train ResNet 50. In this slide, we will study about CNTK scaling up with the help NCCL 2.0. NVIDIA Collective Communications Library, also known as NCCL, provides optimized implementation of inter-GPU communication operations, such as all reduce and variance. Developers using deep learning frameworks can rely on NCCL's highly optimized, MPI-compatible, and topology-aware routines to take full advantage of all available GPUs within and across multiple nodes. NCCL is optimized for high bandwidth and low latency over PCIe and NVLink high-speed interconnect for intra-node communication, and sockets and InfiniBand for inter-node communication. NCCL allows CUDA applications and deep learning frameworks in particular to efficiently use multiple GPUs without having to implement complex communication algorithms and adapt them to every platform. NCCL provides optimal bandwidth on most platforms, saturating NVLinks, PCIe links and network interfaces. NCCL performance tests introduce the notion of bus bandwidth for all supported collective operations to make sure NCCL ran at the maximum theoretical speed. This allowed for performance numbers to be compared with the native hardware characteristics, similarly to what can be done for classical send or receive operations. For example, machines connected through a 10 GB per second network card should be able to perform operations at up to 1.2 GB per second. Advantages of using NCCL with CNTK. 1. Tackle the challenge of designing a scalable and distributed deep learning framework. 2. Efficient intra-node and inter-node training. 3. proven scale-out for GoogleNet up to 160 GPUs. 4. Support for small CIFAR10 or MNIST and large datasets ImageNet. 5. Optimize model propagation and gradient aggregation. 6. Various design alternatives to provide optimal performance for small and large-scale training. Now CNTK comes with NCCL 2.0 support and compatibility GPU accelerated scaling. This was tested and certified by Nvidia for ResNet 50. Microsoft for practical real-life situations where CNTK needs to read other tools, models. So they started implementing support for models in ONNX format. Let us now see CNTK's compatibility with respect to ONNX guidelines. ONNX provides a definition of an extensible computation graph model, as well as definitions of built-in operators and standard data types. This feature is now fully supported by CNTK. Getting ONNX models is as follows. 1. Choose a pre-trained ONNX model from the ONNX model zoo. 2. A lot of pre-trained ONNX models from ONNX model zoo are provided for common scenarios. Convert models from mainstream frameworks. Each computation data flow graph is structured as a list of nodes that form an acyclic graph. Nodes have one or more inputs and one or more outputs. Each node is a call to an operator. The graph also has metadata to help document its purpose, author, etc. Operators are implemented externally to the graph, but the set of built-in operators are portable across frameworks. Every framework supporting ONNX will provide implementations of these operators on the applicable data types. CNTK is also one of the first deep learning toolkits to support the Open Neural Network Exchange (ONNX) format, an open-source shared model representation for framework interoperability and shared optimization. Co-developed by Microsoft and supported by many others, ONNX allows developers to move models between frameworks such as CNTK, CAF2, MXNet, and PyTorch. ONNX is supported by Amazon Web Services, Microsoft, Facebook, and several other partners. You can design, train, and deploy deep learning models with any framework you choose. The benefit of ONNX models is that they can be moved between frameworks with ease. According to Microsoft's Eric Boyd, the ONNX representation offers two key benefits. First, framework interoperability. Developers can more easily move between frameworks and use the best tool for the task at hand. Second, shared optimization. Hardware vendors and others with optimizations for improving the performance of neural networks can impact multiple frameworks at once by targeting the ONNX representation. Let us now check out the various CNTK flexibility features provided in the latest release. CNTK is quite flexible and supports most popular input data formats. First, plain text, for example, UCI datasets. Second, speech formats HDK. Third, images in binary format. Fourth, DSM file format. Fifth, new formats can be added by creating data reader. CNTK provides flexibility to the developers by providing the following features, namely, 1. CNTK has rich API support, mostly implemented in C++ train and eval methods. 2. CNTK has low-level plus high-level Python API. 3. CNTK has R and C# API for train and evaluate methods. 4. CNTK provides UWP, Java and Spark support. 5. CNTK has built-in readers for distributed learning. 6. CNTK has Kerr's backend support. 7. CNTK has model compression that is fast binarized evaluation feature. 8. CNTK now supports CUDA 9 or cuDNN 7. The Microsoft Cognitive Toolkit CNTK supports both 64-bit Windows and 64-bit Linux as platforms. It is recommended you install CNTK from pre-compiled binaries for these platforms. You run CNTK on a Mac using Docker. There are two ways of using CNTK Docker containers. 1. Using CNTK images published at Docker Hub. 2. Building CNTK Docker images. CNTK is available as Microsoft Azure Virtual Machine offerings. The Data Science Virtual Machine (DSVM) can be deployed on either CPU-only or GPU-based VM instances. The Nvidia drivers, CUDA, cuDNN is built into the DSVM. CNTK can support various tasks, such as speech, image, and text, and can try out new ideas quickly. As we move towards core part of CNTK, let us focus on developer-related information like CNTK Github Details. CNTK Github Repository URL is https://github.com/microsoft/CNTK. CNTK Github is maintained by Microsoft developers. It has 1,386 users. It has 16,008 Github stars. 1,246 times repository has been forked by AI developers. CNTK Github has 1. All the source code of CNTK, that is Microsoft Cognitive Toolkit. 2. All the scripts for Linux and Windows binary installers. The CNTK Github repository details are easy to understand and implement, so let us see how it is organized. Microsoft Cognitive Toolkit Github repository apart from source code has 1. All the test scripts for evaluation of check-in workflow on the build server. 2. The tutorials and examples folders contain variety of example configurations for CNTK networks using both the Python API and Brain script. 3. In tutorials folder, you will find several tutorials, both for the CNTK Python API, the Python Functional API, and for Brain script. 4. Documents folder has technical reports, model editing language, network description, language and configuration files, and rest of the general documentation has been moved to Microsoft website. 5. All the Python notebooks related to development and implementation of DNN using CNTK. 6. Pre-trained models folder contains pre-trained models that can be used as DNN featurizers, or as the basis for transfer learning. 7. The tools folders has scripts, which can be used to create an environment for building CNTK from source. CNTK teams have painstakingly documented CNTK website, with lot of information about its usage, and development information. CNTK has a new designed website apart from GitHub portal. The URL is https://docs.microsoft.com/n/cognitive toolkit/. It has got all the latest information about the installation, tutorials, blogs, presentations, and many technical reports. Now let us explore the CNTK examples provided in the website. The Examples webpage is part of CNTK website hosted on Microsoft Docs website. The URL is https://docs.microsoft.com/n/cognitive toolkit/examples. The examples are structured by topic into image, language understanding, speech, and so forth. Now let us explore the CNTK tutorials provided in the website. The tutorials webpage is part of CNTK website. The URL link for CNTK tutorials is https://docs.microsoft.com/n/cognitive toolkit/tutorials. It contains links to Python tutorials, Azure notebooks, and additional Python recipes. You can also try out the tutorials live with pre-installed CNTK in Azure notebooks for free. To get started with CNTK, we recommend the tutorials in the tutorials folder. CNTK has very well documented CNTK Python API and has lot of technical articles published for Python developers. It has got Get Started section for beginners of CNTK enthusiasts. This Python API documentation is hosted on a separate website. Its URL is https://cntk.ai/pythondocs/index.html. It has all the information required for developing and implementing CNTK programs using Python API. This page describes the Python API for CNTK version 2.6. This is an ongoing effort to expose such an API to the CNTK system, thus enabling the use of higher-level tools, such as IDEs, to facilitate the definition of computational networks, to execute them on sample data in real time. Apart from Python API reference, it has layers, library reference, how to extend CNTK for further customization. It has very detailed and fine-tuned webpage for Python developers about how to get started using CNTK for their Python applications. It starts with a good simple basics of setting up and training a network using the CNTK Python API. CNTK team also has published few documents on using BrainScript and CNTK scripts inside CNTK Manual at Github Repository. The Manuals folder of the Github has got the documents related to creating and development of DNN using CNTK. Some CNTK related manual are as follows. 1. How to create user minibatch sources includes source code. 2. How to debug CNTK Python programs includes source code. 3. How to read and feed data includes source code. 4. How to train using the different APIs includes source code. 5. How to create and/or use CNTK learners includes source code. 6. How to create a custom deserializer includes source code. CNTK team also has provided links to very good technical CNTK presentations and webinars in the CNTK website. Presentation section is part of CNTK website's resource section web page. You can find CNTK and deep learning related presentations. It has got links to some popular CNTK presentations by Microsoft data scientists. Now let us move to the crucial part of CNTK, that is, to understand the CNTK deep learning application structure. This simple CNTK example creates a simple neural network with two hidden layers using two input parameters, and finally a computation graph is created and rendered. Sequential is a powerful operation that allows to compactly express a very common situation in neural networks where an input is processed by propagating it through a progression of layers. This operation is known as forward function composition. Forward function composition is an operation that takes two functions, f and g, and produces the function h such that h of x equals g of f of x. Hence, sequential takes an array of functions as its argument, and returns a new function that invokes these functions in order, each time passing the output of one to the next. Every deep learning CNTK application, behind the scenes, follow deep learning principles of generating computational graph before actual prediction or evaluation of the model happens. What you now see is CNTK computation graph. The arrows in the plot show the flow of information. W and B are the weights and bias of the dense layer. The input, X, is used to compute the output of the first dense layer, whose output is used to compute the output of the second dense layer. Model Z as output. This output is in turn used to compute the loss as the squared difference between the target, Y, and Z combined with a specified learner. Gradients will be computed and correctly propagated backwards to the appropriate nodes. In this slide we see logical steps of CNTK sample program. Here in this CNTK's deep learning sample program, you can see typical deep learning application divided into 5 basic deep learning logical sections, namely, 1. Data reader. 2. Deep learning model. 3. Neural network with trainer or learner instance. 4. Invoking of train and eval methods. 5. Finally, predict the result. This is minimal basic deep learning program elements required for creating deep neural networks and apply the activation functions to predict the outcome with certain accuracy, like simple image classification tasks. Let us explore in detail the nitty-gritty of a CNTK deep learning application syntax and its structure. So let's begin with this CNTK Python simple example. In the slide you see simple CNTK program used for classifying data. Here in this code snippet, you see a data reader constructor function which instantiates a minibatch source reader from text stream object constructed from TTF serializer class. This class configures the CNTK text format reader that reads text-based files with specified input dimensions, label dimensions and training flag parameters. Below function LSTM sequence classifier net defines DNN structure according LSTM architecture. This function is invoked later in the program, while creating LSTM model. Now coming to the next part of CNTK Python simple example. Here in this code snippet, train sequence classifier function employs all the process of training and evaluation of model, that includes 1. Creating model. 2. Define training method with specified classifier to compute the probability error, cross, entropy. 3. Define minibatch size and training iterations to be executed using training function. 4. After instantiating of trainer object, get minibatches of sequences to train with and perform model training. 5. Inside the training loop using cross entropy with softmax and classification error, compute the evaluation average and loss average. Return both evaluation average and loss average to the main function. As we dive deeper into deep learning CNTK Python example, we have now reached the code execution point where deep learning compute method and evaluate method of the deep neural network along with model are defined. CNTK invokes the model training and computation of LSTM classification process, prints the accuracy of the model and classification details. In this slide we see the CNTK workflow diagram. CNTK workflow is very simple. Let me explain in brief the CNTK workflow. First step is that CNTK AI developer needs to create a data set by removing noise, converting to lowercase, sorting and tokenize the data. Also split the data into training data set and test data set. This step process is known as preparation of data. Second step is to create an instance of reader to feed the clean data. Third step is to configure the reader with input dimension, the number of hidden layer, and build the model architecture with required classifier, and let's name it as Model Z. Fourth step is to create an instance of deep neural network with classifier and activation function. Fifth step is to define the training method, that is, loss is measured by softmax function using cross entropy, and error is measured by the classification error function. Both these functions are defined. Next, before we initiate the learner instance, we need to create the instance of learner and connect to activation function. Since we feed our model in minibatches, the description and details of minibatch is also included. Before we launch our training, we connect our learner to the model parameters and learning schedules. Sixth step is to compete the trainer function with Model Z, defined loss, error functions and the learner instance. This trainer encapsulates the overall training process and employs one or more learners to tune the parameters of a specified model using gradients of parameters with respect to a training objective. During the training computation, in each training loop, the actual data training batch is loaded to the trainer as features, that is input, and labels, that is output. The model parameter is optimized bit by bit based on our predefined trainer. Moreover, we are also taking records of the loss and error for each loop. The records are used to virtualize the training progress. During these 6 steps, we have trained the model using the training data sets. Testing data sets are not involved during the training procedures. In the 7th step, we will evaluate the performance of our model. We connect our trained models to a softmax layer and evaluate the output based on the input features. The input features are retrieved from testing data set. After the testing step, model displays the predicted label based on our testing data sets. This value is evaluated, and from that we compute and get the results of accuracy of the model. Now the model is ready for prediction for unknown data set. So this is the workflow of a simple CNTK deep learning application. We are now aware of the programming aspect of CNTK applications. Now let us explore operations and execution of CNTK program. CNTK's main operations are as follows. 1. Train a model with the train command. 2. Evaluate a model with the eval command. 3. Edit models, for example, add nodes, remove nodes, change the flag of a node with the edit command. 4. Write outputs of one or more nodes in the model to files with the write command. 5. File operation can be controlled through script languages. In this slide, we will describe the training a model with CNTK. Training a neural network with CNTK involves 3 components that must be configured. 1. Network configuration. The neural network, including its structure or formula, model parameters, needs to be configured. Training criteria and evaluation metric are also included here. 2. Reader. How training data is read by reader is defined and configured. 3. SGD, the hyperparameters of the stochastic gradient process. You need to provide this information through a configuration file as the first argument when calling the CNTK executable. The configuration file uses a specific syntax. In addition, there are other tasks that CNTK supports, such as edit existing models and write node outputs to a file. In this slide, we will describe the evaluating a trained model with CNTK. Once you have trained a model, you can use CNTK Eval library to evaluate the model in your own application. You can also use Python to evaluate a pre-trained model available in CNTK Github Repository. Usually in evaluation step, CNTK evaluates the trained model for classification, accuracy, and eventually use it to make a prediction for new, previously unseen data. So the classification accuracy of the trained model will be computed when trainer walks through each training item and computes the regression probability. After computing the regression probability for the current training item, the program determines the associated predicted 0 or 1 label and compares that Boolean result with the actual class label. Next, evaluate the classification accuracy and the cross-entropy error on the test data. In this way, evaluation of trained model happens. Since CNTK has built-in commands to do the model accuracy, so to evaluate a trained model's accuracy, you use the eval or test command from CNTK library. In this slide, we will describe how to use a trained CNTK model. Now we will see how to use a trained model in your own code. Once you have trained a model, you need the functionality to evaluate the model in your target environment. CNTK provides multiple ways to serve your models in different scenarios. They are: 1. You can use a trained model from C++, Python, C# or other .NET languages. 2. You can run evaluation on your machine or in Azure. Let us check out the CNTK overall train workflow. To summarize, the overall workflow of CNTK program is as follows: 1. Import all packages of CNTK. 2. Write reader function, def create reader path, is training. 3. Write network stage operations. 4. Create model, def create model function. 5. Create criteria, def create criterion function model. 6. Write trainer and evaluator, def train reader, model, def evaluate reader, model. 7. The main functions of deep learning are as follows: 1. Create model instance function, that is, create model function. 2. Create reader instance function with training flag set to false, that is, create reader. 3. Create train instance function, that is, train reader, model. 4. Create reader instance function with training flag set to false, that is, reader equals create reader. 5. Finally, invoke evaluate function to find the model results and prediction, evaluate reader, trainer. From this slide to next few slides, I will explain in detail how the deep learning classification technique is implemented using CNTK. First, let's implement simple Python function to read the CNTK format. For the example purpose, we are going to use CNTK minibatch source, which is specially developed to handle file data. The Python code on the slide does the reading of the data file and return the minibatch source. The code here takes several arguments. Argument 1 path equals the file path where the data is stored. Argument 2 is training equals Boolean variable, which indicates if the data is for training or testing. In case of training, the data will be randomized. Arguments 3 and 4 input dim, num label classes are the numbers of the input features, and the output heart vector size. Those two arguments are important in order to properly parse the file. The first method creates the two streams, which are passed as argument in order to create deserializer, and then for minibatch source creation, the function returns minibatch source object, which the trainer uses for data handling. Once that we implemented the data reader, we need the Python function for model creation. For the iris data set, we are going to create 4 feed-forward neural network, which consists of one input layer with 4 neurons, one hidden layer with 50 neurons, and the output layer with 4 neurons. The hidden layer will contain tanh activation function, the function which creates the neural network model. We will look at it in the following code snippet. As it can be seen, that dense function creates the layer where the user has to specify the dimension of the layer, activation function, and the input variable. When the hidden layer is created, input variable is set to the input data. The output layer is created for the hidden layer as input. The one more helper function would be showing the progress of the learner. The flowing function takes the 3 arguments and prints the current status of the trainer. Once we implemented all 3 functions, we can start with CNTK learning on the iris data. At the beginning, we have to specify some helper variable, which we will use later. Create the reader for data batching as shown in the slide. Then create the deep neural network model with loss and error functions. Here in this code snippet, I will discuss about the trainer activities. Now we define the trainer. The trainer will be with stochastic gradient decadent learner, with learning rate of 0.2. Now we need to define parameters for learning and showing results. As it can be seen that the batch size is set to data set size, which is typical for small data sets. Now we defined minibatch to data set size. The iteration should be very small value, since iris data is very simple and the learner will find good result very fast. Running the trainer looks very simple. For each iteration, the reader load the batch size amount of the data and pass to the trainer. The trainer performs the learning process using SGD learner and returns the loss and the error value for the current iteration. Then we call print function to show the progress of the trainer. In this output code snippet, we do output of learning process. Once the learning process completes, we can perform some result presentation. We plot the loss and error function converted into total accuracy of the classifier. The following pictures shows those graphs. Based on the plotted graphs, inference on the problem is derived by the data scientist or data analyst. Now let me introduce you to distributed deep learning concepts. From here on to next few slides, we explore distributed deep learning concepts. Let me list out CNTK's operations of distributed deep learning. Before starting distributed training, you must provision and configure your computing machines nodes as follows. First, if you run the distributed training with multiple machines, all machines should be configured as same. Second, configure the network for inter-nodes communication. Third, when using GPUs, install, compile and configure the drivers and related libraries CUDA, cuDNN, etc. Fourth, install and set up OpenMP on multiple machines. Fifth, Put the following program.py and data on all multiple machines. It's better to use NFS shared mounted directory and place all files on this directory. 6th, CNTK supports the several types of parallel distributed training algorithms, and here, we're using data parallel, training data parallel, distributed learner, which distributes the workloads along with each mini-batch data, and aggregates or exchanges the results from multiple processes. 7th, when you run on multiple computing machines, nodes, first, you create the following hosts file in your working node. This file lists the computing nodes on which the training workloads will be started by MPI. Here we use only 2 nodes for distributed training. Next you locate the program and data in the shared mounted folder, and make sure that every nodes can access both program and data. 8th, finally, run the mpexec command in your working node. /mnt/test is the shared folder, and F0 is the network interface name on my working node. 9th, before training, CNTK will seek for the InfiniBand network, and it's automatically used if available. Then the training workloads will run on all nodes in parallel, and the results are exchanged. Using Batch AI, the only one command runs all configuration tasks including MPI and inter-nodes communication settings. It significantly simplifies the distributed training. 10th, when your cluster is ready, now you can publish the training job. Before starting your job, you must first create the following JSON for the job definition. With this definition, the command Python train nist_py_dev for training data dev for model output will be launched on MPI on mperon command. Therefore the training workloads will run on all nodes in parallel, and the results are exchanged with each other. 11th, the result, the generated model and console output, is located in the shared mounted folder, and you can download these files. You can also view the results with integrated UI in Azure, Portal or AI tools, etc. Now let me explain briefly about CNTK's distributed training. In CNTK, data parallelism is used to achieve distributed training. Here CNTK distributes each mini-batch over workers, then aggregate the result. The challenge over here is communication cost between multiple GPU and CPU. Hence data parallelism is executed only if computation time is equal to communication time. Suppose, for example, DNN whose mini-batch size is 1024 with 160 million model parameters. So if computation speed is 1 megabyte for every 1/7 of a second, and if communication time is 1 megabyte for every 1/9 second, that is 640 million model parameters over 6 gigabytes per second, then we cannot implement data parallelism with 2 GPUs. So for these kind of scenarios, Microsoft CNTK team has come up with 1-bit SGD algorithm. Here in this technique, it quantizes gradients to 1 bit per value, then the carry-over quantization error to next mini-batch. In this algorithm, CNTK DNN trainer communicate less often, every now and then try to grow mini-batch size on small subset. It is important to note that it has to keep contribution per sample and momentum effect constant. Hence define learning rate and momentum in a mini-batch size agnostic fashion. This technique quickly scales the DNN up to mini-batch sizes of 3000 and can run up to 100,000 samples. Block momentum SGD is a very recent effective parallelization method. Block momentum SGD is the implementation of the clockwise model update and filtering, or BMUF, algorithm, short, block momentum. The goal of this technique is avoid to communicate after every mini-batch, and run a block of many mini-batches without synchronization, finally exchange and update with block gradient. Microsoft used the block momentum SGD and the data parallel 1-bit SGD algorithms to train DNNS and LSTMS on a 2600 hours speech recognition task, and compared word recognition accuracies versus speed-up factors. The tables on the slides and figures shows the results. In this slide we list out CNTK's unique features. CNTK unique features includes: first, a revamped I/O architecture. Second, including more flexible readers for text and speech. Third, making it easier to input popular formats into the toolkit for deep learning training. Fourth, they have also included a growing library of standard components, such as sequence to sequence with attention, and the state-of-the-art deep residual nets for image recognition. Fifth, symbolic loops over sequences with dynamic scheduling. Sixth, turn graph into parallel program through mini-batching. Seventh, unique parallel training algorithms 1-bit SGD, block momentum. Let me list out few more CNTK's features. CNTK other features include optimized, built-in components. First, components can handle multi-dimensional, dense or sparse data from Python, C++ or Brain script. Second, FFN, CNN, RNN or LSTM, batch normalization, sequence to sequence with attention, and more. Third, reinforcement learning, generative, adversarial networks, supervised and unsupervised learning. Fourth, ability to add new user-defined core components on the GPU from Python. Fifth, automatic hyperparameter tuning. Sixth, built-in readers optimized for massive data sets. Efficient resource usage. First, parallelism with accuracy on multiple GPUs or machines via 1-bit SGD and block momentum. Second, memory sharing and other built-in methods to fit even the largest models in GPU memory. Express your own networks. First, full APIs for defining networks, learners, readers, training and evaluation from Python, C++ and Brain script. Second, evaluate models with Python, C++, C# and Brain script. Third, interoperation with NumPy. Fourth, both high-level and low-level APIs available for ease of use and flexibility. Fifth, automatic shape inference based on your data. Sixth, fully optimized symbolic RNN loops, no unrolling needed. Now let me explain briefly about CNTK's batch scheduling of variable length sequences. While CNTK has very efficient built-in readers that take care of many details for you like randomization, prefetching, reduce memory usage, etc., sometimes your data is already in NumPy arrays. Therefore it is important to know how to specify a sequence of inputs and how to specify a mini-batch of sequences. In deep learning, modeling the data often may not fit into memory RAM. For this case, CNTK provides the mini-batch source class. This mini-batch source class provides following functionalities or features. First, a chunked randomization algorithm that holds only part of the data in RAM at any given time. Second, distributed reading where each worker reads a different subset. Third, a transformation pipeline for images and image augmentation. Fourth, composability across multiple data types, for example image captioning. Fifth, transparent asynchronous loading so that the GPU is not stalling while a mini-batch is read or prepared at present, The minibatch source class implements a limited set of data types in the form of deserializers, namely: first, text or basic, CTF deserializer; second, image deserializer; third, speech, HTK speech deserializer, HTK MLF deserializer. CNTK can operate on two types of data, namely: 1. Tensors, that is, n-dimensional arrays, dense or sparse; 2. Sequences of tensors. The distinction is that the shape of a tensor is static during operation, while the length of a sequence depends on data. In CNTK we use axes to mean the same thing as dimensions for NumPy arrays, that is, a tensor of shape 7, 10, 6 has 3 axes. Tensors have static axes, while a sequence has an additional dynamic axis. A dynamic axis is, therefore, a variable length axis. CNTK hides batching from the user. We want users to think in tensors and sequences, and leave mini-batching to CNTK. CNTK has native support for variable length sequences, that is, it can accommodate sequences of highly varying lengths within the same minibatch, without need for workarounds like bucketing. Together with CNTK's notion of specifying the learning rate per sample instead of a minibatch average, every item of sequences of any length contributes the same to the gradient, leading to consistent convergence. CNTK can also automatically batch sequences with different lengths into one minibatch, and handles all necessary padding and packing. Workarounds like bucketing are not needed. The reason we are separating the dynamic axis, batch and sequence from the static axis is because there are only very few operations that affect these axes. Despite our clear definition of minibatch size being the number of samples between model updates, there are two occasions where we must relax the definition. First, in sequential data, variable length sequences do not generally sum up to exactly the requested minibatch size. In this case, as many sequences as possible are packed into a minibatch, without exceeding the requested minibatch size, with one exception: if the next one sequence in the randomized corpus exceeds the length of the minibatch size, the minibatch size will consist of this sequence. Second, in data parallelism, here, the minibatch size is approximate, as our chunk-based randomization algorithm cannot guarantee that each worker receives precisely the same number of samples. To properly understand distributed deep learning, we need to understand CNTK's data parallel training. Specifically, in data parallel learning, minibatches are split across multiple nodes. Each computing node, GPU or machine, computes the gradient of a minibatch. These gradients then have to be summed, and new weights have to be calculated and propagated across the nodes. This process can be very slow because the number of gradients in general equals the number of parameters. Deep neural networks often contain millions of parameters in 32-bit precision, needing to be exchanged in every update step. Essentially, there are two ways of reducing communication overhead for training. First, increasing minibatch size and thus reducing the update frequency, and second, reducing the amount of data to be exchanged between computing nodes for each update. Now, parallelization in CNTK is implemented with MPy, so distribute minibatch over workers, or reduce partial gradients in order to make training distributed CNTK, provides a set of distributed learner that encapsulate a set of algorithms that uses MPy to execute the state. To use data parallel SGD in Python, the user needs to create and pass a distributed learner to the trainer. A distributed learner handles data like gradients or momentums across multiple MPy workers. The only difference is that the user needs to wrap the learner into the corresponding distributed learner and make sure it picks up the data from the minibatch source based on the current worker rank. In order for distribution to work properly, the minibatch loop should exit on all workers at the same time. Instead of writing the training loop manually and taking care of checkpointing and distribution herself, the user can delegate these aspects to the training session exposed through function.train or test methods. It automatically takes care of the following things, namely, 1. Checkpointing, 2. Validation, 3. Testing or evaluation. All that is needed from the user is to provide the corresponding configuration parameters. Let me tell you about one of the important concepts of deep learning, that is CNTK's data parallelism using stochastic gradient descent, strategizing stochastic gradient descent for data parallelism. First, stochastic gradient descent, SGD, a randomly selected training set observation, is used to update the weights of the model. The simplest solution for parallelizing SGD across multiple CPUs or nodes is to have every node read the current parameter values, calculate the gradients using one batch of data, lock the parameters and update them. Second, batch gradient descent. All training set observations are used to update the weights of the model. BGD sums up the errors of all training samples and performs weight updates once per epoch. The formula for BGD is almost the same as for SGD, with the difference that now we sum up the loss of all samples before we perform the gradient update. It better updates but more computationally intensive than SGD. Batch gradient descent has been shown to perform worse for larger training data sets than SGD, often causing overfitting. Third, mini-batch stochastic gradient descent. A subset of the training set is used to update the weights of the model. The most often used gradient descent version nowadays seems to be the minibatch SGD MSGD, a trade-off between the stability of BGD and the noisiness of SGD. In MSGD, weight updates are performed once every minibatch. The minibatch size is an additional hyperparameter to be optimized. The larger the minibatch size, the fewer updates are required, thus making the learning faster. This applies especially to data distributed parallel learning, where every gradient that needs to be exchanged between nodes increases the computation time. On the other hand, making the minibatch size too large generally leads to worse performance and overfitting due to the low stochasticity of the process. However, the researchers clearly show that in order to train neural networks using very large minibatches, we have to fine-tune the learning rate as a function of the minibatch size. As a general rule, it must be accepted that most of these solutions, except for synchronized SGD, modify the training process to achieve parallelism and accept a small accuracy hit as a result. If this hit is not too extreme, the benefit of the speedup can generally outweigh it. Ultimately, you will have to decide if the benefits of the speedup are worth it for you to sacrifice accuracy. One possibility of a compromise is to use heavy parallelism during the development phase and train the algorithm on a single node during final training. CNTK currently supports 4 parallel SGD algorithms. 1. Data parallels GD, data parallel, training with 1-bit SGD class, implements the 1-bit SGD technique 1. This technique allows to distribute each mini-batch over k workers. The resulting partial gradients are then exchanged and aggregated after each mini-batch. 1-bit refers to a technique developed at Microsoft for reducing the amount of data that is exchanged for each gradient value to a single bit. 2. Block Momentum's GD, Block Momentum SGD algorithm is the implementation of the blockwise model update and filtering, or BMUF, algorithm, in short block momentum. It creates a block momentum distributed learner. Block momentum divides the full data set into n non-overlapping blocks, and each block is partitioned into n non-overlapping splits. During training, a random, unprocessed block is randomly taken by the trainer, and the n partitions of this block are dispatched on the workers. 3. Model averaging's GD, Model Averaging SGD algorithm is an implementation of the model averaging algorithm detailed in without the use of natural gradient. The idea here is to let each worker processes the subset of data, but averaging the model parameters from each worker after a specified period. Model averaging SGD generally converges more slowly, and to a worse option, compared to 1-bit SGD and block momentum SGD, so it is no longer recommended. 4. Data Parallelis GD, Data Parallel Training with Parameter Server algorithm. Parameter Server is a widely used framework in distributed machine learning. The most important benefit it brings is the asynchronous parallel training with many workers. It introduces the parameter server as a distributed model store. Furthermore, as parameter servers is a distributed framework that store model parameters. Workers can only retrieve those parameters they need during the mini-batch training process. This brings very good flexibility in designing distributed training method, and also enhances the efficiency when conducting training with sparse model updates. Finally, one of the key advantages of using CNTKs is its ability to scale efficiently across multiple GPUs and machines. With this new update, they are bringing a new technique known as block momentum that takes training scalability to a new level of performance. So we can conclude that CNTK has matured and has come a long way in last 3 years. So in conclusion, we can say that CNTK is production ready. 1. CNTK is production ready, state-of-the-art, accuracy, efficient, and scales to multi-GPU or multi-server. 2. Automatic differentiation, deferred computation, optimized execution and memory use. 3. Powerful description language, composability. 4. Implicit time, efficient static and recurrent NN training through batching. 5. Data parallelization, GPUs and servers, 1-bit SGD, block momentum. 6. Feed-forward DNN, RNN, LSTM, convolution, DSM, speech, vision, text. Performance. 1. Speed, faster than others, 5 to 10x faster on recurrent networks. 2. Scalability, few lines of change to scale to thousands of GPUs. 3. Built-in readers, efficient distributed readers. Programmability. 1. CNTK is Microsoft's open-source, cross-platform toolkit for learning and evaluating deep neural networks. 2. Powerful C++ library for enterprise users. 3. Intuitive and performant Python APIs. 4. C# or .NET or Java inference support. 5. Linux, Windows, Docker, .NET support. 6. Growing use and contribution by various product teams. I hope you got an overview of different deep learning techniques used in AI enterprise applications using CNTK. In my next video, I will be explaining next deep learning framework PyTorch. Please share your comments as it inspires me to do the further topics on machine learning and deep learning videos. Please share this video with your friends and colleagues, and I will publish my next video, Deep Learning Series PyTorch, very soon. Till then, have a nice time watching my videos, and bye.